So we're in the second portion of section 3.2. So today we're going to talk mainly about graphing logarithmic functions. So yesterday when we talked about logarithmic functions, we talked about the relationship between exponential and logarithmic functions. So what did we say? How are these two sets of functions related? What did we say was the relationship between the two? Remember, Harrison? Inverses. They're inverses. Exponential and logarithmic functions are inverse functions of each other. And we're talking about as long as we have the same base. So the functions with the same base are inverses. So on Monday, is that Monday? Yes, on Monday, we made a graph of, and I'm going to just sketch a quick graph again here. So we want to talk about the graph of exponential or of logarithmic functions. So we made a graph of y equals 2 to the x. And we said that exponential functions, and I'll do the 2 to the x in red. Let me put some marks here on my graph. We said that the exponential function, if it's not shifted, it's always going to go through the point 0, 1. And we said that we'll just plot some points, when x equals 1, 2 to the 1 is 2, so y is going to be 2. When x equals 2, we get 2 to the second power, or 4, so we're going to be up here at 4, and when x equals negative 1, we get 1 over 2, or 1/2. So our function looks like this. So a rough sketch of our graph. I just plotted some points. Is going to look something like this. And we said that y equals 0, the x-axis is a horizontal asymptote for this graph, and it's always increasing as long as our base is greater than 1. So if these two functions are inverses of each other, the logarithmic function and the exponential function, what do we expect the graph of the logarithmic function to look like? Mark says down and that way. What's special about the graphs of functions and their inverses? They reflect over the x-axis. There's a line of symmetry. Anybody remember what the line of symmetry between graph of a function and its inverse is? No? They're going to reflect over the line y equals x. So a function and its inverse reflect over the line y equals x. So I think that's what you were getting at, Parker, is that it's kind of go the other way. So if I plot, I'm going to plot, and I'm going to rewrite this in red, just so we keep everything matched up. This is y equals 2 to the x. So in blue, I'm going to plot y equals log base 2 of x. So if I'm just looking at thinking about what it's going to look like, rather than going through the point 0, 1, it's going to go through the point 1, 0. So basically I'm switching the x's and the y's when I graph an inverse function. When x equals 1/2, my logarithm is going to be negative 1. So I'm just switching this point over here. When x equals 2, the logarithm is going to be 1. And when x equals 4, my logarithm is going to be 2. So my graph is going to look roughly like this. And the line y equals x would be right up the middle here, like so. So they're reflections of each other over the line y equals x. So we said any exponential function's graph, if it's not shifted, is going to go through the point 0, 1, and it's going to look more or less like our red graph here. Any unshifted logarithmic function is going to look more or less like our blue graph here. So let's go into a little more detail about the graphs of logarithmic functions. So if we have y equals log base a of x. So all of these properties of the graph come from the fact that these two are inverse functions. So our domain is all real numbers greater than 0. So we're saying x has to be greater than 0. So I can't plug a negative number into a logarithmic function. Our second property is that the range is all real numbers. So the y values are going to go from negative infinity down here. It's going to keep going up and up and up to positive infinity. So our range is all real numbers. The x-intercept is going to cross the x-axis at x equals 1. So our x-intercept is going to be at the point 1, 0. X equals 1, y equals 0. With no, so we have a function that looks like this, with no shifts, no reflections, nothing. The y-axis is a vertical asymptote. And another way of saying the y-axis is the line x equals 0. And our function, logarithmic functions are increasing. It keeps getting bigger and bigger and bigger and bigger. It slows down a lot, but it keeps getting bigger. So our function and this is if our base is greater than 0. So for a positive base, our function is always going to increase. It's going to keep going up and 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 up. So those are our properties of graphs of logarithmic functions. The important ones to remember: the domain is x is greater than 0. So we can't put a negative number into a logarithmic function. Doesn't work. The x-intercept for an unshifted logarithmic function is always at x equals 1. So it always goes through the point 1, 0. And the vertical asymptote is the y-axis, the line x equals 0. So those are the three main things to remember about the graphs of logarithmic functions. And it's, again, comes from the fact that it's an inverse function of the exponential function. So any questions on our properties of our graphs? So really all I want to talk about is how we're going to graph a shifted logarithmic function, and then talk a little bit about the domain. So really not a lot of information today. So if we're going to graph a transformation, if our graph is shifted, the logarithmic functions shift just like any other function that we've already talked about. And I'm going to say shift with the same rules that we are with the same rules as with other functions. Shift with the same rules as other functions. So, and the graph is going to shift if we're asked to sketch a graph, we're going to need to remember that the horizontal asymptote shifts left or right with the graph. And the x-intercept is going to shift left or right, up and down, just like the graph. So the x-intercept shifts by the same amount that the graph is going to shift. So the x-intercept, we can say it shifts with the graph. It shifts the same amount as the graph. So if we know that the graph is shifting left 3 and up 5, we know that that point, the x-intercept 1, 0, is going to shift left 3 and up 5. So we already have, automatically, we have a point that our graph is going to go through. So our horizontal asymptote shifts left or right, because it's an asymptote, it's a, and I shouldn't say, I said horizontal here, I should have said vertical. Sorry. I was thinking of exponential function. We have a vertical asymptote with a logarithmic function. So our vertical asymptote shifts left or right. If I shift the vertical asymptote up or down, it doesn't really make any difference because it's a vertical line. And our intercept shifts with the graph. So for example, if our parent function is log base 10 of x. And we mentioned yesterday that log base 10 is the same as saying log x. We don't have a base, it's base 10. So our parent function is log x. What is going to be, how is this function going to shift from our original? So what's going to be that transformation? Left 2. So we're using the same rules that we've talked about before. Left 2. So our vertical asymptote would shift from x equals 0 to x equals negative 2. Our x-intercept would shift from 1, 0 to negative 1, 0, shift over by 2. So our asymptote and our intercept would shift with the graph. What about the graph y equals log base 10 of x plus 2 minus 1? How is that one going to shift? Down 1. What is it? Left 2. Left 2, down 1, left 2. And our vertical asymptote would shift left by 2. And our intercept, our x-intercept would shift left 2 and down 1. So we'd have our vertical asymptote, and we would have 1 point for our graph automatically. How about y equals negative log base 10 of x? How would that one shift? reflect over the x. And then how about y equals log base 10 of negative x? That one's going to reflect over the y-axis. And our asymptote would reflect, and our intercept would reflect just like the graph does. So the same rules that we've been using before to shift logarithmic functions. So I want to take a look at sketching a graph of this second one. So we're going to sketch a graph of y equals log base 10 of x plus 2 minus 1. So any questions on shifting before we move on? Okay, so we're going to sketch. Our problem is, we're given a problem that says sketch a graph of log base 10 of x plus 2 minus 1. So we're going to sketch. And when I say, and I'm just going to say y equals, log, when I don't have the base here, that means log base 10. So here are my axes. When I have a problem like this, these problems should not be too tough. So we know that normally an unshifted logarithmic function has a vertical asymptote along the y-axis. We said this shifts, just a second ago we said this shifts left 2, down 1. So our our vertical asymptote is going to shift from x equals 0 to x equals negative 2. So I'm going to have a vertical asymptote. My asymptote is going to shift over here to negative 2. So my graph is going to come up here from negative 2 like so. And I'm shifting down 1. Normally my graph is going to have an x-intercept at x equals 1. Well, I'm going to shift over by 2 to the left. So I'm going to go over to negative 1, and I'm going to go down 1. So my intercept is shifting over and down with my graph. So I have the point negative 1, 1. Sorry, negative 1, negative 1. And my graph is going to go through that point. So normally my unshifted exponential function, just a quick sketch, would look like this. So I've shifted it over and down.
So that's what's the point? That's how you would graph. So you moved it to negative 1, but what's the original point?
The original point is 1, 0. So an unshifted exponential function goes through 1, 0. Our x-intercept is 1, 0. So I shift that point over by 2. So I go over 1, 2 to negative 1, and then down 1.
Okay,
so that point just shifts over just like the graph.
Is this how you wanted that to work?
Yeah. And if we wanted another point on our graph, if we had our calculator, and we'll talk more about calculating logarithms, I could plug in x equals 0 here. In my calculator, calculate the log of 2 and subtract 1, and I would get the point where it crosses the y-axis. Yes?
Is there no horizontal asymptote?
No, because we said it's increasing. That's a good question. So it kind of looks like maybe there would be a horizontal asymptote, but it's increasing, so it just keeps going. It'll keep going up and up and up and up and up. It just gets very, very, very flat, but it does keep going up forever.
All right.
So it's not very steep, but it just keeps going up. So there is no horizontal asymptote. Well, that's a good question because it kind of does look like there would be one. So this is how I would sketch a graph of a shifted logarithmic function. The asymptote shifts and my intercept shifts. What if the problem asks us to find the x-intercept of this shifted function? So where it crosses the x-axis. Anybody have an idea of how we would find the x-intercept? What's that? Switch the x's. That's how we find inverses. If we set x to 0, that would give us our y-intercept. So we set y to 0. To find the intercept, to find the x-intercept, I should say, we want to figure out this point. We know what the unshifted intercept is, but if the problem asks us to find the x-intercept of the shifted function, to find the x-intercept, we set y equal to 0 and solve for x. And we know how to do that now. So I'm going to say that log of x plus 2 minus 1 equals 0. We can't do it quite yet. So I'm going to get the logarithm by itself. I'm going to add 1 to both sides. Log of x plus 2 equals 1. Now I'm going to write this in exponential form. So what's the exponential form of this equation? 10, and then let's write the whole thing out. 10 to the 1, the base to the 1, equals x plus 2. So 10 equals x plus 2. Subtract 2, and x equals 8. So my graph is not quite accurate because this point should be over at, if I drew an accurate sketch, this point would be at 8, 0. So if the problem asks you to find the x-intercept, set the function equal to 0, and then switch it to exponential form and solve for x. So we know how to do that. We learned how to do that yesterday. So I know my graph didn't turn out, the scale of my graph isn't quite right, but we get the idea. And we mention it really briefly. If we plug in x equals 0, if I put in x equals 0, that would give us the y-intercept. X equals 0 on the y-axis. All right, questions on what we did with this graph? So these are the kinds of questions that the homework will ask you about graphing logarithmic functions. Shift the asymptote, shift the intercept. If it asks you to find the x-intercept, set the function equal to 0, rewrite it in exponential form, and solve for x. All right, one last thing. One last thing for today, and then we're done. Finding the domain. Finding the domain is not a difficult problem.
Just finding the domain of the graph.
Of a logarithmic function. Finding the domain of a logarithmic function. So let's say we have f of x equals the natural log x plus 3. Just a minute ago we talked about the domain of the logarithmic function. What did we say we couldn't plug into a logarithmic function? A negative number. It can't be less than 0. So to find our domain, we have to make sure this, whatever we're plugging into our function, is positive. So how do we write that in math symbols? Positive means How does it compare to 0? Greater than 0. So to find the domain, I'm saying whatever I'm plugging into the function is greater than 0. So the domain of this function is x plus 3 greater than 0. Solve for x. Subtract 3, x greater than negative 3. So to find the domain of an exponential function, you're saying whatever you're plugging in, whatever's in the parentheses, is greater than 0. And then you solve for x.
So it can't be negative, but negative 1 is greater than
The whole parentheses can't be negative. So if I plug in x equals negative 1 here, I would get 2,
Yeah,
so natural log of 2.
Yeah.
If I plug in negative 3, I get 0.
Yeah.
But if anything less than negative 3, then I end up with a negative.
Yeah. Got
Okay?
it.
So the domain just means whatever is in this parentheses has to be greater than 0. So when we're finding the domain, whatever's in that parentheses has to be greater than 0. Any questions? All right. Our homework is the problems that we left off from yesterday, which was page 216, number 33 through 38, 39 through 55, odd, plus I'm going to give you a worksheet. The worksheet, the problems on the front side of the worksheet are like 5-second problems. Switching from exponential to logarithmic form, or switching from logarithmic to exponential form. On the back side of the worksheet are some graphing problems. We're going to skip the last 4 graphs. Because they're kind of complicated. So we have an hour to work. So I'm looking for, by the end of the period, I'm looking for either all the book work to be done plus some of the worksheet, or all the worksheet to be done. The worksheet really is like a 10-minute activity on the front side. The problems are just switching from exponential to logarithmic form really fast. So while you're working, I'll pass your test.